Thank you. Um, Hi, this is Zhijian Q. I'm an assistant professor in Xiamen University. I'm glad to be here to present you Meshfree framework for seismic response of assistance as a representative of our research group with Professor Ahmad Elkma as a PI and Professor Jess Chen as a co-PI from UC San Diego. Here's the outline of the presentation. I will briefly introduce RKPM-based Meshfree computational framework, RKPM-2D, and UCSD Sawyer constitutive models. After that, I will show several seismic loading applications using the RKPM-2D and UCSD Sawyer models. Lastly, I'll provide conclusions and our future research. So our research was motivated by the large liquefaction-induced flow failure of the lower San Fernando Dam during 1971 San Fernando earthquake. So to increase our understanding of this problem, the main challenge to adjust and model include large deformations, crack propagation, and the multi-scale strain localization phenomenon. Particularly in light of performance-based earthquake engineering, and we need to more accurately assess consequences of very strong seismic shaking events. So here are two examples of large deformation ground failure by other researchers. The first one is evaluation of the lower San Fernando Dam using the finite difference program FLAG by Chaudhary, and the second example is landslide analysis using a material point method by Professor Soga. As you can see from these two figures, that the large deformation ground failure and the shear band developer can be observed. So in summary, our aim lies in developing a more reliable analysis tool for a wide range of performance-based earthquake engineering and the related consequences when strong shaking and large deformations occur. So on this basis, I want to introduce RKPM-based Meshfree computational framework, the reproducing kernel particle method, RKPM, by Professor Chen and Professor Liu, has been recognized as an effective numerical method for solving partial differential equations. It can model large deformation, high gradients, crack propagation, multi-scale strain localization phenomena. Currently, RKPM has been successfully applied to a number of challenging engineering problems by Professor Jess Chen. Here's an example showing 3D slope failure by Professor Chen. Recently, an open source 2D RKPM-based Meshfree computation framework. You can check the website to download this. For linear elastostatics was provided with many attractive features, such as boundary condition specification, reproducing kernel shape function generation, and domain integration with stabilization. So our research goal is to bring the capabilities and the advantages of this RKPM 2D computational framework for use in earthquake engineering applications. So our research will build on this public RKPM 2D, so which is only for linear static analysis by extending the RKPM 2D to conduct dynamic analysis, development of large strain modular with crack propagation, implementation of UCSD OpenSea Sawyer constitutive models, inclusion of multi-layer profile analysis. Finally, we will use the new Meshfree computational framework to conduct representative seismic response simulations. Ultimately, we will provide an open source Meshfree 2D MATLAB-based large deformation computational tool for conducting nonlinear 2D static or dynamic analysis for geotechnical and soil structural in action earthquake engineering applications. So here I want to introduce several UCSD Sawyer constitutive models which have been implemented into the extended RKPM 2D. The first model is pressure independent multi-year surface model for organic soils or clay on the fast loading conditions. As you can see from this figure, for the soil response on the cyclic loading, the plasticity only exhibits in the deviatoric stress plane. The volumetric stress and the strain response is linear elastic and is independent of the deviatoric response. So the second model is strain softening model for sensitive clay, cemented soil, verdant soil, over consolidated soil, or frozen soils. This model extends the pressure independent model with a new strain softening logic. These two figures show representative of strain softening behavior of soils under cyclic loading. The third model is cyclic softening model for stiffness and the strength degradation of soils due to pore pressure buildup. As you can see from this figure, as increase of excess pore pressure ratio, the stiffness and the strength of the soil will decrease. So I will show several seismic loading applications using the extended RKPM-2D large deformation and the UCSD soil constitutive models. The first example is an earth stem. It has 3 zones, zone 1, zone 2, and zone 3, which is foundation without any strain softening. The peak strength of zone 1 is higher than zone 2. The input motion was simply taken as 1994 Northridge earthquake ground surface Renati receiving station record. This figure shows the particle model. So this figure shows the initial soil state. As you can see, the horizontal displacement, vertical displacement are tiny. The vertical stress and the shear stress are increasing along depths before shaking. So this figure shows longitudinal displacement with time. As you can see, the displacement contour at the 3 seconds, 6 seconds, 9 seconds, and 15 seconds about the progressive failure and the large downslope deformation. So this figure shows the shear strength contour, gamma XY. As you can see, the shear strength and the crack propagation from the bottom to the top of the model. Also the contours at the different time. So this figure shows the acceleration and the lateral displacement time history of representative points R1, R2, and R3. As you can see, the acceleration of points R2 and R3 were isolated due to the strain softening behavior of soil. The displacement of R1, R2, and R3 are increasing as time during shaking. So the second example, it shows a simple example of pi soil in action. So we just specify a relatively rigid material inside this box, essentially representing the pile. So you can see the overall deformation with time at 3 seconds, 6 seconds, 9 seconds, and 15 seconds. So this figure shows the shear strength contour. So you can see the shear strength and the crack propagation stop due to the pile restraining effect. The last example is a shallow foundation in soft clay. Similarly, we specify a relatively rigid material in this blue zone, representing the shallow foundation and the tower. The red zone here is soft clay. You can see the soil response cyclic degradation as the increase of pore pressure, the strength and the stiffness decrease. So this figure shows the vertical displacement with time. You can see the vertical displacement is increasing during shaking. This figure shows the shear strength contour. You can see the foundation failure and strain localization near the foundation. So that's the seismic loading application. So I will provide conclusion and our future perspectives. We propose to bring the capabilities and advantages of the Meshfree method with a dedicated open source framework RKPM-2D for use in earthquake engineering applications. So overall, the employed computation framework has the potential to evaluate seismic performance of soil systems under earthquake loading. So our future research is underway towards liquefaction analysis of saturated soils, using OpenSea's PDMY03 material and UP formulation, and the inclusion of structural components like a beam column element with fiber section, and the performance-based earthquake engineering assessment frameworks under conditions of strong excitation. So as the development continue, a wide range of practical application will benefit from this effort and the potential future developments. We will also provide UMAT option to allow users to include their own constitutive model available to all members of peer and earthquake engineering communities. So the drawback of this RKPM-2D computational framework is computationally expensive. The public RKPM-2D was implemented in MATLAB, so our research have to build on this version of MATLAB, but we are thinking to convert the code to Fortran or C++ to make the analysis faster in the future. So if you are interested in this RKPM-2D large deformation computation framework, you can go to this website, soilquake.net, to download this framework. That's all about my presentation. Thank you for listening.